Hello students, here is MITALI Rai and you will be with me for the next 30 minutes. Today we will continue with the digital electronics. Last class already we have covered the introduction part and number system already I have completed. Now I will complete the logic gates, combinational circuit, and also in number system I will complete the fractional conversion. So let's start from this fractional conversion. So the first we will start with our decimal and binary. So binary to decimal and decimal to binary. Already two examples are given in the screen. I am giving you another example. Let's in binary one term is present, that is 0.011. So how to convert it into decimal number? So in binary number, after the decimal point, the weightage of means the positional weights of all the digits are like this, like 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, like 2 to the power minus n. So what we have to do? We have to multiply each bit with all their positional weights. That means point term will be like this. This point term will be remain like this. Then after this 0 will come and it will be multiplied with its positional weight, that is 2 to the power minus 1. Then plus. Then this 1 will come, 1, and that will be multiplied with 2 to the power minus 2. And then this 1 will come and it will be multiplied with 2 to the power minus 3. Then we have to add all these values and that is our, let it is x. So this x is our required decimal number with base 10. Here base is 2 and here base is 10. So one example is given in the screen. The question is 0.1011 and it is multiplied with their positional weights, that is 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, 2 to the power minus 4, and again we have to add all this sum, and finally the answer is coming like 0.6875 and the base is 10. So this is binary to decimal conversion. Similarly, we have to go for decimal to binary conversion. So what we have to do in the same way, suppose I will take one example, that is, this one is now decimal to binary conversion. So now I am taking one point, that is 0.25. So what I have to do here? I have to convert this decimal, means base is 10, into binary, means the base will be 2, means x base 2. So I have to multiply this 2 with all these digits, that means I have to multiply here 2. So now I will be getting 0.50. Okay. So then again this 1 will be like this. We have to separate this 0. Then again with this term I have to multiply with 2. So now it is coming 1.00. So I have to multiply with 2 until all these terms are coming 0. So now here after decimal all the terms are 0. So now our process is over. So now I have to go from this side, means the reverse of our simple conversion. We have gone from MSB to LSB. Now we will go from this side. So now our answer will be 0. This is our first term 0. This is our second term 1, and here base is 2. So now this is our decimal to binary conversion. In the same way, one example also given here, that is 0.131, this is our binary term, and this is 0.3125 is our decimal number, and here the decimal to binary conversion is shown in the example. So next we will go in our next slide, again the fractional conversion, but this is octal to our decimal and decimal to octal. So in this case what we have to do? So here in place of binary, the number system is octal number system. So what I have to do? First is converting octal to decimal. Octal to decimal means already I have told you in the last class, the number of digits will be 0 to 7. Let's here I have taken 0.71. So here this is 1 and 7. Okay. So now this is our octal representation. Octal. So I have to find out its equivalent decimal representation. So what I have to do, again I have to multiply with their positional weight, means this will be multiplied with 8 to the power minus 1 and this will be multiplied with the 8 to the power minus 2 and it will go on like this. So what will be our answer? This one is 0. So now what I have to do, this is point, this is 7 into 2 to the power 8 to the power minus 1 plus 1 into 8 to the power minus 2. Here the answer is, this is point and this is x and its base will be 10. After multiplying we have to add what will be the answer, that will be our equivalent decimal representation. Already one example is given and you have to do it by your own. Similarly next is decimal to octal conversion. Decimal to octal conversion. So what we have to do here, suppose I will take that, I can take that example, that is 0.23. Here base is 10. I have to find out the equivalent octal fractional number. Let that number is x and here the base will be 8. That means now I have to multiply it with 8. What is the base? So what is the answer? 0.28. I have to multiply 0.23. I have to multiply with 8. So now it is coming 1.84. So I have to separate this one. Again I have to go for the multiplication and here I will be getting 6.72. So again I have to separate this one 6. So then again I have to multiply with this 8 and here it is coming 5.76. So in this way I have to multiply until it is 0. Otherwise if it is not coming 0, then I will continue it up to 2 or 3 bits. So now again I have to go in this way. So what is the answer? 0.165. So our answer will be, this x will be equal to 0.165 and the base is 8. So in this way we have to go for octal to decimal and decimal to octal. That example is already given in the screen. Next I can go for the next fractional conversion, that is hexadecimal to decimal. Hexadecimal to decimal. So here what I have to do, this one is our hexadecimal. So hexadecimal means the base is 16. In the same way, first hexadecimal to decimal means, in that question it is already given 54.D2. Here base is 16. I have to find out what is the equivalent decimal representation, means base will be 10. So what I have to do, again I have to multiply with their positional weightage. So here its positional weightage is 2 to the power 16 to the power 0, as it is hexadecimal. So it will be 16 to the power 0, it will be 16 to the power 1. After decimal it will be 16 to the power minus 1 and it will be 16 to the power minus 2. So in the similar way, I have to multiply each digit with their positional weightage. I have to put the decimal point here like this, and again I have to all these factors combinedly. What the answer will be coming, that will be our equivalent decimal representation. Similarly, when I have to go for decimal to hexadecimal, decimal to hexadecimal, suppose here one term is 70.71. This is in hexa binary, this one is our decimal representation. I have to find out what is the equivalent hexadecimal representation. So what I have to do, in the same way, already I have told you in the previous example, I have to multiply this 16 with this bit until it is coming 0, and so in the same way I have to go for multiplication and I have to separate the digit which is which is before this decimal point, and again I have to go for in this way. Already you can see that example. In that example, it is multiplied with 16, and here before decimal it is coming 3. In the second multiplication it is coming 14. In the second it is coming 11. And I have to find out what are the equivalent hexadecimal notation. So in this way I have to go for our fractional conversion. So next, another thing is, suppose one term is, this is the one way from hexadecimal to binary number system. We can go from hexadecimal to decimal or octal to decimal, or then I can convert those decimal numbers to the equivalent binary numbers. Otherwise, in other way, I can directly write like this. Suppose one decimal number is here, that is 71. This is our decimal number. I have to convert it into its into octal number. So what I have to do? Its octal representation means this point will be like this point. Then 7 will be octal, means 3 bits will be there. So 1 1 1 1. 1 means for 1 another 3 bits will be here. So 0 0 1. So our final answer is 0.111001. 001. This is the equivalent octal representation. Similarly, when I will go for this from this decimal to hexadecimal, then I have to represent all these numbers in 4 bits. So what I have to do? So here the point will be remain like this point. 7 will be represented as 0 1 1 1, and 1 will be represented as 0 0 0 1. So this is our final hexadecimal representation. This is the another or shortcut way of fractional conversion. In this way also we can go for fractional conversion. Next is our logic gates. So these are some logic gates which are in our syllabus. First is our OR, NOR, AND, NAND, XOR, XNOR, buffer and NOT. This NOT is also known as inverter circuit. Okay. These logic gates are used to go for simplify the calculations. So first I can start from this. These are their equivalent representation and diagrams. So first I can go for this one is our buffer circuit. Okay, this is buffer circuit. In buffer circuit, what will be the representation? So this one is our input side and this one is our output side. So what will happen here? If this is, we will give 0 here, then in the output side we will be getting 0. If we will give 1, in the output side we will be getting 1. So just this one is our NOT or inverter. This one is our NOT or inverter. This one is our input side. This one is your output side. So what will happen here? So this is the truth table will be like this. If we will give here input as A, then in the output side we will be getting A bar, means complement of A. That means what will be the input? Just reverse of that in the out, we will be getting as your output. If we will give 0 here, we will be getting 1. If we will be getting 1 here, we will be getting 0. So this is the truth table for our buffer and inverter circuit. Okay. So next is our OR and AND circuit. So what about our OR and AND? So OR circuit is like this. Okay. So this one is, let 2 inputs are here, 2 input and 1 output circuit get. So A, B are 2 inputs and here will be getting Y as output. So in case of OR, the expression is A plus B. A plus B. And the truth table will be like this. This one is A, B and this one is Y. So if what are the different inputs? Already we know in binary number system the inputs are 0 0, 0 1, 1 0 and 1 1. So here what will happen? OR means addition, simple addition. So here if we will add 0 plus 0, we will be getting 0, 0 plus 1, 1, 1 plus 1, 1 and 1 plus 1 is also 1. So that means if all these inputs are 1, then finally we will be getting the output as 1. If all the inputs are 0, then we will be getting 0. If any one of the input is 1, then we will be getting 1 as the output. So this is the truth table for OR. This one is for OR. Okay. So now for AND. So next is for AND. So what is AND? So here this is the gate. Here is A and here is B, and in the output we will be getting A dot B. This is the multiplication. A dot B means this one is A, B and this one is Y. So in the same way the input are 0, 0, 0, 1, 1, 0 and 1, 1. So what we will be getting here already, the first one is here AND 1. So in case of AND means both the terms should be true, means both the terms should be 1. If both are 1 or true, then the output will be true or 1. If any one is 0 means false, then the output will be 0, because this is the multiplication. If we will multiply 0 with any term, the output will be 0, means false. So this one is 0, 0, 0 and the last one is 1, already given in the slide. So next coming to XOR and next coming to NAND and NOR and NAND gate. NOR means one N will be added here, NOR. Okay, that means what is NOR circuit? The same OR circuit followed by one inverter circuit, means same OR circuit followed by one inverter circuit. So what will be the resultant circuit diagram? This will be our resultant circuit diagram. And here this one is A, B and this one is Y. So what will happen here? As at the output one inverter circuit is given here, means just the reverse. So output will be here. What is the output here? A plus B. So here it will be A plus B bar. A plus B bar. So what will be the truth table? Just reverse means thus complement all of this output. This means this is A, B and this will be Y. So what will be the output? 0, 0, 0, 1, 1, 0, 1, 1. Here the output was 0. So here we'll be getting 1. Here 1. So here 0. Here 1. So here 0. Here 1. So here 0. This will be the truth table. So similarly next for NAND. NAND means N and N for this NOT gate means the inverter. Again this circuit will be followed by one inverter circuit, means the diagram will be, this is our AND gate, these are the two output inputs as A and B, and here one inverter circuit will be here. That means now our circuit will be like this. So this one is Y, this is A and this is B. So what will be the output? What is the output? We have got here just reverse of those outputs, means A, B and Y. Okay. So here 0, 0, here 0, 1, 1, 0 and 1, 1. Previously in AND case, what we have got? 0, 0, 0 and 1. So in NAND case, reverse of this output means complement of this output. That means reverse of 0 will be getting here 1, reverse of 0, 1, reverse of 0, 1, reverse of 1, 0. So these are the truth table for OR and NOR and NAND gates. These are the required truth table. Next we will go for our XOR gate, XOR and XOR gate. So what is this XOR and XOR gate? XOR gate is written there. So what is this XOR gate? XOR gate. First is XOR gate. Okay. So the gate is like this. The diagram is like this. Okay. So this is the output Y. This is A and this is B. And it is represented as A dot B. This is our XOR gate. So what is the truth table? So here this is A, B and here it is Y. Okay. So again we will take the same input like 0, 0, 0 1 1 0 and 1 1. So what is the output here we will be getting? XOR means, and here all of see, so first is 0 0. In XOR we will be getting, if we will give same input, means if both are 0 then we will be getting 0. If both are 1 then we will be getting 0. If we will give dissimilar input then we will be getting 1, means true. Okay. So what is the representation here? It is A bar B plus A B bar. We can find out individually and we will be getting this as our output. So next is XNOR. XNOR, what will happen here? The diagram will be like this. This is our diagram. So XNOR, one buffer circuit is added here. So the diagram will be, the truth table will be just reverse of this. That means what will be the truth table? What we have got here, just complement of that one. Means this is A, B, and here we will be getting A XNOR B bar. So that is AB plus A bar B bar. Okay. So here we will be getting 0 0 0 1 1 0 1 0. Just reverse of this. Means 1 0 0 1. This will be the truth table. And already this is also given in the screen. So this is all about our digital electronics, what is in your syllabus or course. So now already I have told about the logical symbols, Boolean expression, truth table, what will be the input and what will be the output. So one thing just I want to add, how to add all these bits. Okay. So that will be required in this calculation. It will be difficult to remember all these things. So you can simply know how to add all these bits. Suppose we will add 0 and 0. So here we will be getting 0. This is simple addition. Okay. So if we will add 0 plus 1, then we will be getting 1 here. This 1 is the sum and 0 is the carry part. Similarly, this one is the sum and 0 is the carry part. Okay. If we will add 1 and 1. Okay. So now we have to add this one. So what we will be getting here? This is 1 1 will be 0 and here 1 will be carry. This is carry bit. And this one is our sum. So these are the simple addition. We have to add all these bits like this. Okay. So now this is not required for you also. You just have to remember all these things. And next, if you have any queries, then any doubts, then you can contact me on my WhatsApp number. That is 9778719239. Thank you.
झीटीए तो माटी आम सामाजिक और पारिवारिक जीवनर मूल कथाटी से माने आगकू गले आगकू जीव संसार आम झील माने और पुओंकठू पछरे नाहंती एबे तो बदली गलानी समय बदली गलानी जुग से झील माननकू आहुरी आगकू नहीं आत्मनिर्भरशील और स्वावलंबी करने ओडिशा सरकार सुदक्षा योजन सरकारी ITI माध्यम संपूर्ण मागणार जोगई देउछंती सबु प्रकार उत्कृष्ट मानर वैषयिक ज्ञान कौशलर तालीम एबे आम झील रहिबे सबुठू आगरे सबुठू उपरे
मु सफल मु कुशली मु सुदक्षा